The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams. And today, we're going to get back into our series on the Fermi paradox. Why is it that humanity, in spite of the vastness of the universe and the statistical likelihood, we assume, of life, has not found any evidence of intelligent civilizations out there? Now, in previous episodes, we looked at various theories, including the possibility that there is no intelligent life out there, known as the Hart-Tipler conjecture, that there is something that prevents basic life from evolving into more complex life forms, and or achieving a degree of technological mastery that would make them easy to detect, known as the Great Filter Hypothesis, to the possibility that civilizations out there are being periodically wiped out or simply avoiding contact with one another, otherwise known as the Berserker probe scenario and the Dark Forest hypothesis. Well, today we're going to explore the Waterworlds hypothesis. Now, this is not to be confused with the Ocean Worlds hypothesis, which we will address in a forthcoming episode, so stay tuned for that. To break it down, the Waterworlds hypothesis conjectures that perhaps on many planets in our universe, water is overly abundant. And while this hypothesis was not inspired by the movie Waterworld, released in 1995 and starring Kevin Costner, the name is applicable because the scientific research that has gone into inspiring it does call to mind a lot of the ideas and themes in that movie, that in fact our entire planet could be covered in water, thus making life extremely difficult for the vast majority of life forms here. However, the origin of this hypothesis is largely the product of recent exoplanet discoveries, but it does have foundations that go back several decades. And this includes David Brin's seminal paper that he released in 1983 titled The Great Silence, The Controversy Concerning Extraterrestrial Intelligent Life, in which he said, "Water covers over 70% of the Earth's surface, yet perhaps the Earth is towards the dry end of the habitable class of worlds. A much smaller land area, or a lack of dry land at all, would afford little opportunity for the evolution of tool-using species. Most intelligent species in the universe might possess the outlook of whales and never conceive of radio or travel to the stars." In this respect, he anticipated discoveries that were made decades later. The current census of exoplanets has now reached well over 5,000, and scientists have noted that for many, the size, mass, and density estimates that they obtained indicated that many of these planets were composed of volatile elements, which is to say, elements that have a low melting point, chief among which would be water. And this presented astrobiologists with a bit of a conundrum. All this time, scientists have considered water to be a key biomarker or biosignature, in the sense that it's something that all life, as we know it, needs in order to exist. And based on the fossil record and the evolutionary timeline that we've managed to reconstruct here on Earth, we also know that the first life forms evolved in water. In particular, around hydrothermal vents. The most recent evidence has indicated that fossilized bacteria dated back to over 4 billion years ago emerged as a result of these deep-sea fissures and vents. Microbial life forms were able to get the necessary energy and elements from the planet's interior that are essential to life as we know it. And of course, the Earth's hydrological cycle, it helps maintain the conditions of habitability upon which all life depends. And of course, all terrestrial organisms need water in order to properly metabolize their food and also ensure that they don't die of dehydration and maintain bodily temperatures. So water is the key to life. However, there is a growing body of research that suggests that too much water may actually be an impediment to the evolution of life. In 2016, the Pale Red Dot team, who actively searched for rocky planets around M-type red dwarf suns, they determined that of the many recent findings, which included Proxima b, Assuming that these are, in fact, rocky bodies that don't have a particularly dense atmosphere, they concluded that water likely made up 50% of the planet's mass fraction, which would mean that it is most likely an ocean planet with a frozen icy shell on top. And in addition, a similar study from researchers from the University of Bern, they examined the formation of rocky planets around red dwarf suns, and their results indicated that these planets could range from being 50% to 1.5 times the size of Earth, and that 90% of the cases, water would account for more than 10% of the planet's mass. And consider the fact that on Earth, water only accounts for 0.023% of our total mass. So once again, you've got a Waterworld scenario. And then you have the case of the TRAPPIST-1 planets, which consists of 7 rocky planets orbiting a red dwarf sun, and multiple studies have indicated that it is likely rich in terms of water. And a 2018 study by Arizona State's School of Earth and Space Exploration calculated the water content, and based on their results, they found that these planets could range from 15% of water by mass for those that were closer to the star and therefore drier, while the outermost were likely 50% water by mass. And last but not least, another study conducted in 2018 by a team of researchers from Harvard University. They examined data from the Kepler Space Telescope and the European Space Agency's Gaia Observatory to try and come up with an estimate of how common water worlds are. And they did this by creating a model that showed the relation between an exoplanet's mass and radius, and they found that planets that have a radius 2.5 times that of Earth and a mass of about 10 times that of Earth are most likely to be water worlds, where water is roughly 50% of the mass. And so far, the exoplanet census has indicated that 35% of all known exoplanets out there are larger than Earth and up to several times the mass, aka super-Earths, and therefore should be very rich in water. Now, what this would mean for the evolution of life as we know it? Well, the implications could be very significant in that planets like Earth that have the right kind of landmass to ocean ratio are quite rare, thus echoing the rare Earth hypothesis. And for example, in a 2018 study, Harvard professor Abraham Loeb and Dr. Manasavi Lingam, they conducted a series of simulations that examine the role played by oceans and continents in the emergence of life, which is something scientists considered a foregone conclusion, that both are necessary in order for there to be species diversification and evolution. And in the end, they came up with 2 likely scenarios. On the one hand, their calculations indicated that a balance between oceans and land masses is crucial to the emergence of complex biospheres. And furthermore, that planets such as Earth, which has a 3 to 7 landmass to oceans ratio, is probably quite rare in our universe. And so, looking for stars within habitable zones, especially around M-type red dwarfs, which appear to be very, very good at forming rocky planets, as indicated by finds like Proxima b, the TRAPPIST-1 planets, Ross 128b, Luton b, Gliese 667cc, and the list goes on. And these are all planets that are within roughly 40 light years of Earth. So in each of these cases, wherever there is a planet that's several times the mass of Earth, the likelihood that it is a water world is strong. And this would mean that, yes, not only does it lack the crucial balance that some scientists believe is absolutely necessary for life, land masses and oceans coexisting, but it would likely have an effect where the planet would become what's known as an ice ball planet. So for those planets that are particularly large and have a large mass fraction of water and are also missing a dense atmosphere, then the outer shell of the planet is likely to be composed of solid ice with an interior ocean floating beneath that. But lower than that, you'd have water that is at such great depths and such great pressures that it would solidify. And so you'd have this big layer of ice between the liquid ocean and the rocky and metallic core, which would mean that there wouldn't be exchange between the core and the ocean itself. Any hydrothermal vents that could exist down at the rocky core would be unable to send their chemicals and their energy and their heat up to where it's needed the most, into that ocean. For those planets that do have a dense atmosphere, on the other hand, well, the same problem applies. If their mass fractional water is high, and if they're particularly large, then yeah, once again, you have a layer of solid ice between the rocky and metallic core and the liquid ocean, which is going to make it very difficult for life as we know it to take root. So, of course, one can see how this would be a proposed resolution to the Fermi paradox, and that is that perhaps most rocky planets that you will find out there in the cosmos will in fact be covered in oceans so very deep that life does not have a chance to emerge on the ocean floor, and no continents for life to eventually migrate onto and start diversifying and creating a rich and varied ecosystem. So it is a fascinating theory, and it happens to fit certain facts, and it's backed by research that has come out in recent years thanks to the huge explosion in terms of the number of confirmed exoplanets out there. But there are limitations to it. There are criticisms that are also supported by a great deal of exoplanet research, as well as the fact that the current exoplanet census is limited. For example, of the 5,690 confirmed exoplanets to date, that is to say, as of the recording of this episode, roughly 30% fall into the super-Earth category, whereas 66% fall into either Neptune-like gas giants or Jupiter-like or super-Jupiter exoplanets. Only 203, which works out to about 3.5%, have been confirmed to be Earth-like, in the sense that they are terrestrial and are comparable in size, mass, and density to Earth. And right off the bat, this demonstrates something about our current methods and their limitations. Because of all the planets that have been discovered out there, almost 3/4 have been discovered using the same method, the transit method, which consists of monitoring stars for periodic dips in brightness, which can indicate the presence of a planet. And if astronomers note that these dips in luminosity are consistent, that they happen with a regular period, then they know that they're looking at an exoplanet, and they can also derive highly accurate estimates on its size. And when it's combined with the radial velocity technique, where stars are monitored for how they move about in place, which is an indication of the gravitational pull on them, i.e. from orbiting planets, astronomers are able to measure with a fair degree of confidence what the exoplanet's mass is. And by comparing mass to size, they're able to obtain estimates on density. The problem is that the transit method mainly works for particularly large planets, hence the prevalence of super-Earths in the census. And the radial velocity method, well, so far, it has turned up plenty of super-Earths as well as gas giants, because these are likely to have noticeable perturbations on their star. And what is considered the best way to study and characterize exoplanets, known as the direct imaging method, which I'll explain in more detail later. To date, the vast majority of planets detected using this method have been gas giants that have a more distant orbit from their star. To find Earth-like planets, that is to say, smaller terrestrial planets that orbit more closely to their suns, which are believed to be the best candidates for habitability and for supporting life, you need much more sensitive instruments, as well as coronagraphs, which are instruments that block out the light from a star so that orbiting exoplanets would become visible. And they'd be visible as small points of light, which is caused by light reflected by the planet's atmosphere surface. And from this, astronomers can gain spectra. They can see how that light that is passing through the atmosphere is broken down into different wavelengths, and from that infer chemical composition. And this is what is meant by direct imaging. In addition, you can also look at the surface there and detect which wavelengths of light are being radiated, and if, in addition to infrared light, heat, the colors that are being radiated are in fact within the green wavelength of the spectrum, then scientists have conclusive proof that there's vegetation on a planet's surface. And that is known as the green vegetation edge, which scientists use routinely using Earth observation satellites to study the extent and health of plant life here on Earth, as well as phytoplankton and other photosynthetic organisms that live in the ocean. And the same is true of plant life that relies on retinal photosynthesis, where they absorb light at different wavelengths from chlorophyll-based plants, and they radiate the color purple. So yes, looking for green and purple planets requires much more sensitive instruments. And we are now in a position to do that thanks to telescopes like the James Webb Space Telescope, thanks to its advanced optics and highly sensitive infrared sensors. And it will also be possible with the upcoming Nancy Grace Roman Space Telescope, which will have the same kind of sophisticated optics as the Hubble Space Telescope, its direct successor, but with the ability to explore several hundred times more planets at a time. And it will also be equipped with a coronagraph to assist in direct imaging studies. And astronomers are also looking forward to the Nancy Grace Roman Space Telescope working together with James Webb by leveraging Roman's ability to survey countless stars and look for exoplanets at a time. With the James Webb's superior infrared sensitivity, they anticipate that the number of confirmed exoplanets is going to grow exponentially, and that the characterization of those planets will also proceed very quickly. So from this, the exoplanet census is likely to grow by leaps and bounds and become far more complete, which is to say, we're going to get a much better idea of the types of planets out there, just how common certain types are. In addition to that, there's been several studies that have cast doubt on water worlds and whether or not they are in fact unlikely to be habitable. For instance, in 2018, geophysicist Edwin Kite and astrophysicist Eric Ford, they produced a study titled Habitability of Exoplanet Water Worlds, and showed that water worlds could in fact maintain a carbon cycle without geological activity or land masses, and therefore produce life. And whereas this carbon cycle wouldn't be the result of tectonic activity, as it is on Earth, Kite and Ford, they conducted simulations that showed that water worlds would be able to cycle enough carbon between the atmosphere and the oceans to maintain a stable climate and thus be potentially habitable. A similar study was released in 2018 that also showed that plate tectonics aren't necessarily vital for maintaining habitable conditions on a planet, so that stagnant lid planets, where the entire surface and mantle consists of one piece, could in fact still maintain a carbon cycle without the need for convection and volcanic activity. And of course, all of this runs into the same old question of principles, whether the Copernican principle or the anthropic principle is in fact the case. And to recap, the Copernican principle argues that Earth is neither special nor unique in terms of its nature or in terms of its position in the universe to view things, and that therefore Earth is likely to be representative of the whole. In contrast, the anthropic principle asserts that scientific observations are only possible because the laws of the universe are compatible with the development of sentient life. And from this, cosmologists who embrace the anthropic principle, they accept that, in fact, humanity and Earth are indeed in a privileged position and are not typical of the norm. And these two principles are, of course, extremely relevant here because they are at the core of the very debate regarding the Fermi paradox. Either Earth and life as we know it is rare or unique, or it is not. And the only way we're really going to be able to address that and the fundamental arguments here that are part of the Waterworlds Hypothesis and every other attempted resolution of the Fermi paradox is to be patient and await the returns of more data and for more exoplanets to be discovered and confirmed and for their characterization to take place. Once we have a better idea of the kinds of planets that are out there and how many of them are truly likely to be habitable, and even show indications of being habitable thanks to the aforementioned methods of characterization, only then can we really know if Earth is typical or atypical of the whole. In other words, are Earth-like planets with life that we would recognize, are they statistically significant out there? And if so, what does that say about the odds of us ever making contact with any of them? So once again, unfortunately, this resolution does not offer a resolution per se, but is nevertheless a very interesting theory that helps astronomers constrain their searches and presents a possible explanation as to why we have yet to find any evidence of life out there. And so we include it here in our ongoing series about the Fermi paradox and the many, many resolutions that have been offered and attempted over the many decades since Fermi first asked the question. And as I mentioned earlier, while this hypothesis is distinct from the ocean worlds hypothesis, which we'll get into next time, it nevertheless has some very interesting commonalities. There's some overlap in it, especially where we were talking about ice ball planets with a frozen outer crust and a liquid water interior surrounding a rocky and metallic core. But we must save that for another time because it's a whole nother theory and it really deserves its own full treatment. In addition, we will soon have the final episode in our Great Migration series that addresses how human beings may someday live in the trans-Neptunian region, which is to say around Neptune on its largest moon Triton, Pluto, Charon, and other quote-unquote minor planets in the outer solar system and the Kuiper Belt. So stay tuned for all of that. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.